Hey guys, today in this video we shall see the concepts behind the methods to determine slope and deflection of beams and also the important formulas. Let's start with the double integration method. This method is applicable to prismatic beams. So what is a prismatic beam actually? The beam which is having the same cross section throughout its entire length, and the center line of that beam is horizontal and straight throughout. So that is called as a prismatic beam, and double integration method is applicable only to prismatic beams and the beams having constant flexural rigidity. So flexural rigidity means product of Young's modulus and moment of inertia, and the beam should have constant flexural rigidity, that is EI value, at any cross section. The bending moment equation valid for entire span. For example, say the bending moment equation at X section, so that equation will be valid for entire cross section, entire section at any length of that beam. So bending equation is constant throughout the entire span. So bending moment equation has to be valid for entire span. When these three conditions satisfy, then we can use double integration method. Now let's see the equation to use the double integration method. This is the equation actually. EI is into d square y by dx square equal to mx. Mx is the moment at x section, and EI, that we know, flexural rigidity, and d square y by dx square. When we integrate this term, we will get dy by dx, so that is slope. And again, upon integrating, we will get y value. Y is nothing but the deflection. So upon integrating two times, we will get slope and deflection. So that's why it is called as double integration method. So it is applicable to prismatic beam only and having constant flexural rigidity, and the bending moment equation valid for entire span. For example, say the simply supported beam subjected to UDL over entire span. So this type of beam can be solved through double integration method. Now let's move on to next method. Next is the Macaulay's method. This is advancement of double integration method. This method is also applicable only to prismatic beams, and also the prismatic beam also have what constant flexural rigidity, as we have already seen in the double integration method. But here we can have discontinuous loading, unlike double integration method. In that previous method we should have continuous loading, or we can say like UDL over entire span. So like that, continuous loading should be there, or we can say symmetrical loading type of general loading should be there in the double integration method. But in Macaulay's method we can use beams which is subjected to discontinuous loading. For example, say in this beam we have point load at free end, and we have UDL at somewhere in the mid of the beam. So this type of loading is called as discontinuous loading. When we see this type of loading with the beam having prismatic section and constant flexural rigidity, we can use Macaulay's method. So the Macaulay's function is given by x minus a power n when x is greater than a. When x is less than a, then Macaulay's function becomes 0. So x minus a power n is the Macaulay's function, and UDL or UL has to touch extreme n. So here you can see, here the UDL is somewhere mid of the beam, but when we have to use this Macaulay's function, then UDL has to be extended over up to the end of the beam, or the extreme end. And for extending that UDL, the same negation shall be applied below, so that we can get the equilibrium. So UVL or UVL has to touch extreme end. This is one point regarding Macaulay's method. And let's see the equation. So this is a general equation that is applied for Macaulay's method. So EI d square by dx square is equal to RA into x. RA means reaction at end A, for example. So this equation is a somewhat generalized one. It will vary for every beam. So this backslash is the separator, so up to which we have to calculate. Like if x is less than a, then up to RAX is calculated. Only when x is greater than a, this function x minus a power n, this will be valid. This cannot be negative. So that's why x minus a will be valid only when x is greater than a. And the constants of integration, when we integrate this equation, we will get constants of integration, that is c1 and c1 plus c2x, like that. So those constants of integration has to be added only after the first term. For example, in this equation we have RA into x, so RAX plus C1, so RAX plus C1 plus C2x. So likewise we have to add the constants of integration after the first term only when we calculate for slope and deflection using Macaulay's method. So we have learned the Macaulay's method, when it is applicable, and what is the Macaulay's function. Let's move on to the next method. Next is the Mohr's moment area method or area moment method. So it will be applicable to non-prismatic beam as well. So in the previous methods we have seen only prismatic beam is applicable, but in Mohr's area moment method we can even use non-prismatic beams. That is, the cross section may vary at different portions. So that is called as non-prismatic beam. And similarly we have variable flexural rigidity at some sections. So constant flexural rigidity is not needed, and we have to ensure that there is a continuity of slope. That is, there should not be any internal hinge or internal links to be present. So when there is internal hinge or internal links, then there will be some discontinuity of slope. Then this Mohr's area moment method will not be applicable. So we have to ensure that continuity of slope is there existing. We can apply this method when area of BMD and the CG of BMD can be found very easily. When we can find the area of bending moment diagram and similarly centroidal or center of gravity of BMD diagram, then we can use Mohr's area moment method when point of zero slope and zero deflection are well known. So for example, zero slope and zero deflection. For example, we say in the cantilever beam we have zero slope in the fixed end. So if we know where is the point of zero slope and zero deflection, we can easily use Mohr's area moment method to solve for slope and deflection of that beam. Now let's see the equations and theorems. We have two theorems here. First theorem relates to slope. So what is the slope between two sections? That is, for example, here you can see this is the end B and X is the section. So slope between these two sections, that is theta B minus theta X, is nothing but area of M by EI diagram between X and B. So what is M by EI diagram? What is actually M? M is the moment, and moment by flexural rigidity. So area of this diagram between X and B gives the slope between B and X, that is theta B minus theta X. So this is the theorem 1, and similarly we have theorem 2 that deals with the deflection. Deflection at B about X. So deflection at B about X is nothing but moment of area of M by EI diagram between X and B about B. So this is the M by EI diagram. So what moment of area about that diagram or about that point B between X and B gives the deflection at that end B. So these are the two theorems that are followed in Mohr's area moment method, and Mohr's area moment method will can be applicable as well to non-prismatic beam, variable flexural rigidity, and when area of BMD, CG of BMD can be found easily, and when the point of zero slope and zero deflection are well known. So if these conditions are satisfied, then we can use Mohr's area moment method. In this method we have two theories. One theory is regarding the slope, another theory is regarding a deflection. Now let's move on to the next method. Next is the conjugate beam method. This method is also applicable to non-prismatic beam. Again, it is also applicable to the beams having variable flexural rigidity at sections. And here we can notice internal hinge or links can be present, unlike in the previous method. In the Mohr's method in the Mohr's method, we should ensure continuity of slopes. So that's why there should not be any internal hinge or links. But in conjugate beam method, that problem is rectified. So we can have internal hinge or internal links. And when area of M by EI diagram and CG of M by EI diagram can be found easily. This is somewhat similar to the previous Mohr's method. Here also similarly we have two theorems. First theorem deals with the slope, second theorem deals with the deflection. So slope in real beam is nothing but shear force in the conjugate beam at that section. So slope in real beam, like if we have a cantilever beam, then slope in that cantilever beam at some section xx is nothing but the shear force in conjugate beam at that same section. So this is the first theorem, and second theorem deals with the deflection. And similarly we have deflection in real beam equal to bending moment in the conjugate beam at xx. Now let's see what is the conjugate beam, how we have to transfer or transition the real beam to conjugate beam. So let's see these 2 points before moving to real to conjugate end conditions. Shear force diagram of conjugate beam represents sloped curve for real beam. This point is similar to the first theorem. And second point is bending moment diagram of conjugate beam represent deflection curve. So this is nothing but deflection in real beam is equal to bending moment in the conjugate beam at that section. So in the same way we have bending moment diagram of conjugate beam, which is representing deflection curve for real beam. So these 2 points have to be noted. And what is a conjugate beam? So we have to transition the real beam into conjugate beam. So how to do that? When the real beam containing roller or hinge support, then in order to get conjugate beam we have to change it by hinge or roller. And when real beam having a free end, for example say a cantilever beam having free end, then that free end has to be changed to fixed end, and fixed end has to be changed to free end. So these are some vice versa. And if beam is having intermediate support, here you can see this is the intermediate support in between the beam, then we have to transfer into a internal hinge to form the conjugate beam. If we have internal support or intermediate support, then that intermediate support has to be transitioned into internal hinge as a conjugate beam. And vice versa, if we have internal hinge in the real beam, then that has to be changed to intermediate support in the conjugate beam. So this is how we have to construct the conjugate beam and find the shear force and bending moment diagram. And shear force represents the slope and bending moment represents the deflection. And this is applicable to non-prismatic variable flexural rigidity at cross sections, and as well as the internal hinge and internal links. Now let's move on to the next method. This is the strain energy method. This method is applicable to the beam which is linearly elastic when Hooke's law is valid and temperature is constant. When these 3 conditions are satisfied, and also the supports are unyielding. The support should be unyielding, and we can even use non-prismatic beam and curvilinear beam. What is a curvilinear beam? It is like a half arch or arch like a beam structure. So that is a curvilinear beam. Curvilinear beam is also a non-prismatic beam. So we can apply non-prismatic beam and which is linearly elastic, and Hooke's law is valid, and also the temperature is constant throughout its length. Then we can use strain energy method. Now let's see the formulas for strain energy. Due to bending moment we have integration mx square, that is moment at x sections in square, dx divided by 2ei. So mx square dx by 2ei is the strain energy due to bending moment. And due to shear force we have xx square dx by 2ar into g. So s is nothing but the shear force, and ar is the reduced area at that section due to shear, and g is the rigidity modulus. So due to sf is given by this formula, and due to axial force, that is p, so px squared dx by 2ae. Here a is nothing but axial rigidity, ei is nothing but flexural rigidity. And due to torque, in the same way, t square dx by 2gip, where ip is the polar moment of inertia, or we can even denote this term as j, that is 2gj. So these are the formulas for strain energy. So first we have to find the strain energy at that section, and then we have to use Castigliano's theorems. So Castigliano's theorem states that the deflection is nothing but the partial derivative of strain energy with respect to the load applied. So then we can get the answer for deflection. And the next formula is the partial derivative of the strain energy with respect to the moment. So that gives the slope value. So first step, we have to find the strain energy at that section due to moment or shear force or axial force or torque. Accordingly we have to find the strain energy, and partial derivative of strain energy with respect to load and with respect to moment gives the deflection and the slope respectively, as per the Castigliano's theorem. And we have, in the same way, we have a unit load method. This is very easy. Deformation is given by integration mx into small mx dx by EIX. So where mx is nothing but the bending moment equation in the concerned segment of the structure due to externally applied loads. So for example, we have a cantilever beam. So say for example, this is a cantilever beam and we have some UDL load and a point load somewhere here, and we have to find at this section the bending moment. Then that will be called as mx, and mx, that is small mx, is the bending moment expression in the concerned segment of the structure due to unit load alone. So what is the unit load? This UDL and this point load has to be removed and apply only the unit load, and due to this unit load, what is the mx equation, that we have to find out. And just to substitute in this formula, that is mx into mx dx by EIX. IX is the moment of inertia at that section, because we can use non-prismatic beam, so that's why moment of inertia may not be constant. So at that section, what is the moment of inertia, that we have to find out, and then find the deflection by using this integration. So this is called as unit load method, and unit load method is clearly defined graphically by this in this video link has been given in the description box. Please also see this video for the clarity to obtain the unit load method. Now let's move on to other methods. We have superposition method. This superposition method is valid only for elastic material. It says the effect of all forces on slope or deflection is nothing but the algebraic sum of all the individual effect. For example, if you see in this propped cantilever beam subjected to UDL, here we have to find if we want to find the RB, that is reaction at NB, then we know what is the formula for deflection at NDB due to UDL, and similarly we know what is the formula for deflection at NDB due to point load at end. So when we just add both the things together, we will get the answer for reaction. So this method is called as superposition method. Similarly, we have another thing, Maxwell's reciprocal method, that is nothing but deflection at point 1 when load is at point 2 is equal to deflection at point 2 when load is at point 1. So when a load is here and the deflection is here, when the load is at that deflection, then what is the deflection here? So this is a ratio, that is deflection at point 1 when load is at point 2, that is deflection at D when load is at C, is equal to deflection at C when load is at D. So this is the Maxwell's reciprocal method. So these are some of the methods that needs to be studied in the slope and deflection of beams. Now let's see the important formulas that we have to remember. Now let's see the formulas for slope and deflection of general beams. So for cantilever beam, first let's consider a cantilever beam subjected to a moment at its free end. Then what will be the slope and what will be the deflection, or we can say maximum deflection. So slope is given by ml by ei and deflection is given by ml square by 2ei when a cantilever beam subjected to moment at free end. Similarly, we have cantilever beam subjected to unit load at free end. So when cantilever beam subjected to unit load at free end, then what is the slope and deflection value? Theta is given by PL square by 2EI, and deflection, that is maximum deflection, is given by PL cube by 3EI. These formulas has to be remembered when we have to find reactions or the slope or the maximum deflections. And when cantilever beam subjected to UDL, then slope is given by theta is equal to WL cube by 6EI and del is equal to WL power 4 by 8EI. And similarly, we have triangular loading. When this type of loading is occurring, then theta is equal to WL cube by 24EI and del is equal to WL power 4 by 30EI. In the cantilever beam, only at the free end there will be deflection. At fixed end, the slope and deflection will be 0. Now let's move on to simply supported beam. So simply supported beam subjected to moments at both the ends. Then what will be the slope and deflection? Slope at both the ends, that is, for example, say this end as A and this end as B. Slope at A and B are same, that is nothing but ml by 2EI, and we have del max, that is deflection, maximum deflection occurring at the midpoint of the section, that is ml square by 8EI. And the moment is applied only at one of its end, then theta A, that is this end, that is A end, ml by 3EI, and the other end will be theta B, that is ml by 6EI. And here the del max is nothing but ml square by 9 root 3 EI when a simply supported beam subjected to moment at one of its ends. And next is the simply supported beam subjected to concentrated point load at mid of its section. So central point load, then what is the theta? PL square by 16 EI, and maximum deflection is PL cube by 48 EI. When it is subjected to UDL, then WL cube by 24 EI is the slope, and deflection is 5 by 384 WL for 4 by EI. These formulas are very important, as that needs to be noted. And when subjected to triangular loading like this, then theta A and theta B are same, that is nothing but WL cube by 120 EI, and maximum deflection is given by 5 by 192 WL for 4 by EI. And when subjected to central moment or the central couple, then theta A and theta B will be m0 L by 24 EI, and at theta C, that is slope at this center, will be m0 L by 12 EI. But the point to be noted is deflection at this central point will be 0, because the deflection will be like this. So then deflection happening will be here and here only. Deflection at center will be 0, but slope at center will be given by m0 L by 12 EI. This is the point needs to be noted. Next, move on to next beam. Next is the fixed beam subjected to point load at the center. Here we have theta A and theta B as 0. Why? Because it is fixed. At fixed end, slope will be 0. And theta max is given by 1 by 192 PL cube by EI. And similarly, we have UDL over the fixed support. Here also theta A, theta B 0. And del max is nothing but 1 by 384 WL for 4 by EI. So these are the important formulas that we have learned. And the question for you is the ratio of maximum deflection of a fixed beam subjected to central point load. Fixed beam subjected to central point load, what is the maximum deflection? And in the same way, what is the deflection in the ESE beam, that is simply supported beam? So what is the ratio between them? That we have to find out. So please comment your answers in the comment sections. And in the same way, we have second question, ratio of maximum deflection of a fixed beam subjected to UDL to that of a simply supported beam subjected to same UDL. So what is that ratio? Please comment your answers in the comment section right now. Thank you for watching this video. If you like this video, please like, comment and share with your friends. Thank you.